Okay, I wanted to take you guys through a review of balancing redox half reactions. And this is just right, I copied this right from your textbook, page 830 and then page 831. So these are the steps that you take. And the easiest thing I think to do is just to take you through an example. So this is question number 24 in the end of chapter questions. And they're asking you to balance this equation in an acidic solution. So it's a redox reaction because oxidation states are changing. So if I just go ahead and write oxidation states here, I have a +3 for nitrogen, a -2 for oxygen, a +6 for chromium, a -2 for oxygen, and I'm hoping at this point you know how to figure these out, right? But just in case, if you have the dichromate ion, the sum of the charges is going to be a -2. Oxygen is almost always a -2 unless it's in a peroxide form, which is like an H2O2, and then it's a -1, or like an Na2O2, then it's a -1. So here it's a -2, so we have -14. So in order to make this equation work, we would need a 12 here. Now because there's two chromiums, we would divide it by 2, so each one would have a charge of +6. So that's on the reactant side, and then on the product side we have the Cr +3, we have a nitrogen which is a +5, and an oxygen which is a -2. So if I'm figuring out which ones got reduced and which ones were oxidized, the nitrogen went from a 3 to a 5. So because that is an increase in oxidation state, I'm sorry, hold on, I want to write the whole species out here. So NO3, NO2, sorry, minus, that went from a +3, and then on this side we went to an NO3 minus +5. So because again the charges increased, that means that got oxidized. So this one is an oxidation half reaction, which again, remember, it loses electrons. So when something loses an electron, we're not going to do this yet, but the loss of electron would be on the product side here. So remember, we always write plus electrons even though they're considered negative. So you would subtract that number. Okay, the chromate is the one that got reduced then. One has to get oxidized and another one has to get reduced. It could be the same species, but in this case they're different. So you have Cr2O7, 2 minus. We have a +6 here going to a smaller charge here, so that's a reduction in charge, which would be, it means it gets reduced, which would be Ger, gaining electrons, which again, if I wrote the electrons, it would be on this side, to gain electrons. Okay, so that's step 1. Step 2 is then you're going to balance elements other than hydrogen and oxygen. So if I look at my first half reaction, I have the same amount of nitrogens on both sides, so that's good. My second half reaction, I have 2 chromates on the left side and 1 on the right side, so I'm just going to put a 2 here. So now I'm balanced. So that's A here. And then I'm going to balance my oxygen atoms by adding water. So on the first half reaction, I have 2 oxygens here and 3 there. So I'm going to add 1 water molecule. Sorry, I'm getting kind of squished here. So now I have 3 oxygens and 3 oxygens. I'm good. On my reduction half reaction, I have to add 7 waters. So step 1, write the half reactions. Step 2, balance all elements other than hydrogen and oxygen. Step 3, balance oxygen by adding water as needed. Next step is you're adding hydrogen to balance out the hydrogen that you added from the water. So here on this side I have two waters, so I have 2 hydrogens, so here I'm going to put 2H+. And then in this equation right here I'm going to put 14H+. So it's kind of a lot of steps, right? So you might want to just have a tab, and labeled in case they do ask you to do something like this. Okay, and then, whoops, sorry. So that's all done. Now we have to add the electrons as needed. So this is where we have to be super careful because it's really easy to make a mistake. So all we want to do is make sure our charges are balanced. I'm just going to get rid of the oxidation states so that they don't throw us off here. Throw me off, really. So here on the left side, I have a total charge of -1. Here I have a total charge of -1 + 2, so I have a +1. So if I have a +1 on the product side and a -1 on the reactant side, I'm going to need to add 2 electrons. So remember NO3, it's an ion, so it stays together, so the whole entire thing has a -1 charge. So I added 2 electrons to cancel out that hydrogen there, so now I have a -1 on this side and a -1 on that side. Okay, the same thing I'm going to do here. I have 14 and 2, which gives me a +12. Oops, I forgot to put that. So here I have a +12. Here I have a +6. So here I'm going to have to add 6 electrons. So I add 6 electrons here. So now my charges, my half reactions are balanced with respect to charges. Okay, so now what I have to do is I have to make sure that the total number of electrons gained are equal to the total of number of electrons lost. So what I can do is I can multiply the first half reaction by 3. So I have 3 waters, 3 nitrates, 3 nitrates. That turns into, I'm just going to erase that hopefully, that turns into 6 hydrogens, and that turns into 6 electrons. So my electrons lost are exactly equal to the electrons gained. So now I'm going to add up my half reactions, and I can get rid of and reduce, just like what we did with Hess's law, I can reduce the amounts of water. So here I have 3 waters and 7 waters. So what I'm going to do is I'm just going to get rid of that, and I'm going to turn that to 4, just because I'm kind of running out of room. And then here I have 14 hydrogens and 6, so I'm going to end up with 8 hydrogens there. So now I'm going to add the reactions together. So I'll just start with those 8 hydrogens there, plus Cr2O7 2 minus, and as I'm doing this, I'm really hoping that my total charges are going to be the same on both sides. My electrons go away because they cancel. 3NO3 minus plus 2Cr plus 3 plus 4H2O. Okay, so that's my overall reaction, but now I just want to make sure that my charges are the same on both sides. So here I have a -3, here I have a -2, and here I have an 8. So my total charge on this side would be +2. No, I'm sorry, +3. 5 minus 8 is +3. And then on this side I have a +6 and a -3, so that would be a +3. So I did it right. So the overall reaction would be this one right down here. Okay, so to tie into the multiple choice, I just wanted to kind of review all of that with you before we talk about this problem, which was number 35. So number 35 is also a redox reaction, and what you're looking at is the way it would be is this is the permanganate ion, and they use this quite a bit for an indicator because it's bright purple, and it'll be appear colorless until the Mn+2 is formed, and then the Mn+2 is a very light pink. So you know when you've reached complete neutralization or complete titration, not neutralization, is when the solution is a light pink. So the way this would be set up is you have your permanganate ion in the burette here, so just my picture right here. So this would be the known solution, the titrant, so they would know the volume, you would know the molarity. And what you're trying to do is you're trying to figure out the concentration of the hydrogen peroxide. So they gave you kind of the concentration in this particular problem, but I just kind of wanted you to understand the lab setup. And the hydrogen peroxide is in an acidic solution, so it could be any acid, it doesn't really matter. So you have this unknown hydrogen peroxide in an acidic solution, and you're titrating it with a known amount of permanganate to figure out the concentration of the hydrogen peroxide. So at the halfway equivalence point, which is what the problem is asking you, halfway equivalence point is when you got rid of half of the number of moles. So if you started with 10 moles of hydrogen peroxide, which you did in this case, half of that would be 5. So you are definitely looking for 5 molecules of hydrogen peroxide. If it was fully titrated, then there would be 0 hydrogen peroxides left, because this is not equilibrium, this is a straight up reaction right here. So if I look through the problems right here, I actually did this screencast already, but I made a lot of mistakes, so that's why I'm redoing it. So if you look at this, you have 1, 2, 3, 4, 5, 6, so that's not right. So titration is precise. So precisely the halfway equivalence point would be half. This one as well, you have 1, 2, 3, 4. So A and B are actually completely out of the question, which is usually the case. We usually left with 2 that seem very reasonable. So C, we have 5 hydrogen peroxides, and D, we also have 5 hydrogen peroxides. The question is, which one best represents the mixture? Which one best represents the mixture? So if you just look at the stoichiometry in the balanced equation right here, you have 5 hydrogen peroxides. When you have 5 hydrogen peroxides, you have 2 Mn plus 2s. So the reason the answer is C is because of that. Now, if you look at answer D, it looks like it's reasonable because you have the same amount of Mn and MnO4. But really, when you're looking at a titration, you really only care about like the main species that's being neutralized. So we're comparing the hydrogen peroxide with this one. Really, the MnO4 is probably could be added in excess. And ultimately, the molar ratios don't make sense anyway. So again, we're looking at precisely the amount of moles. So anyway, hope that helps.